So, hello friends, I Dr. Mohan L Verma, Professor and Head Department of Applied Physics, Sri Shankaracharya Technical Campus, Bhilai. Welcome you all in this lecture number 7.3 of the series CSV2 Physics. Learn with me. This is lectures on some special topics of BTech Physics. The title of today's lecture is Wave Packets and Heisenberg's Uncertainty Principle. Outlines of these lectures, the objectives and prerequisite of lectures. This is the first object outline. Second, the concept of wave packet. This is the new concept. And uncertainty principle. This is the third topic which I will cover in detail. And because this topic is very important as far as the quantum physics is concerned. These topics actually entirely completely differentiate the quantum physics and the Newtonian physics. And finally, I will summarize this lecture. Objectives and prerequisite. The objectives of this lecture is to introduce the concept of phase velocity, group velocity, and the wave packets. And then second objective is to describe Heisenberg's uncertainty principle and its mathematical interpretation. To understand completely this lecture, the prerequisite for this lecture is the basic knowledge of de Broglie's concept of matter wave, the wave function, and the probability density. And these terms have already been covered in previous lectures. And the law of superimposition of waves. And this is the topic related to interference of waves. And some basic ideas of the use of trigonometric functions. And the students should have also the knowledge of differentiation as a mathematical tool. Now let us start from the concept of wave packet. This is the new topic and the new concept, so little bit typical. So far we have covered the concept of matter wave, that is actually the wave associated with a moving body, and to interpret that matter wave we have completed the concept of wave function and the probability density to give the probability of the existence of any particle at a particular position at a particular time, and the wave equations, that the Schrodinger's wave equation, and time dependent and independent form. So we have covered all these terms related with this de Broglie's matter wave. But now let's talk about the velocity of the matter wave. So in general, the velocity of wave, it is calculated by its phase velocity. And for the calculation of phase velocity, here we will perform a simple mathematical derivation. So let's have a plane wave of frequency nu, where this omega is angular frequency, and the wavelength lambda, which can be correlated with the propagation constant or wave constant k, that is 2 pi by lambda, and this is traveling in along x direction shown by this curve. So mathematically one can write this function as y is equivalent to exponential of I kx minus omega t, and this is similar to that wave function we have used in terms of psi, and that kx and omega t again with minus and we have earlier used, and further we have converted this in terms of energy and momentum there. So here we can calculate this phase velocity by using this phase term, which is taken as constant, kx minus omega t is equivalent to constant. So when we solve this for x is equal to constant plus omega t by k. Then let's convert this x position in terms of velocity. So we will differentiate this with respect to time. So we will have dx by dt. This is represented by vp, which is the wave velocity termed as phase velocity. And so dx by dt, this is equivalent to omega by k. And when we put this omega is equivalent to 2 pi nu and k is equivalent to 2 pi by lambda, then finally we will have this phase velocity vp is equivalent to nu multiplied by lambda. So this is the general relation we have used so many times in physics, where we correlate with the velocity with frequency and that wavelength. And many times we tell about this, that frequency is inversely proportional to wavelength, and this is that when this velocity is constant. So let's talk about the velocity of the matter wave, that is de Broglie's wave, by using that phase velocity terms. So that particle matter has a dual nature, particle and wave. According to de Broglie's hypothesis, we have this is the wavelength that is known as de Broglie's wavelength, lambda is equivalent to h upon p, where this p is the momentum. We can replace by mv, so lambda is equivalent to h upon mv. So we have different form of this relation in terms of energy, and that energy is converted for different type of particles. So h is Planck constant, m is mass, and v is the velocity. But this v is the velocity of that particle. Now we will use that energy terms, that E is equivalent to energy of particles, where for quantum condition this E is equivalent to h nu, and we have this Einstein's mass energy relation, E is equivalent to mc square. When we compare these two, E is equivalent to h nu and E is equivalent to mc square, we have this nu is equivalent to mc square by h. So this is the frequency, and when we use this relation for that phase velocity derived in the previous slide, that Vp it is equivalent to nu lambda. So this nu Vp is equivalent to nu lambda. So this is the nu, and when we put this mc square by h here and lambda from this relation, then mc square by h multiplied by h nu, and that is equivalent to c square by v. Since this v, this is the velocity of the particle, so obviously always this velocity of particle will be less than c. So this the velocity of de Broglie wave is represented by u here. This will be greater than c. So let us see again this v. This is the velocity of that particle, and obviously this will be less than c, and this is c square by v. So this u, this will be first greater than v, as well as this is greater than c. So because the particle velocity v must be less than the velocity of light c, so de Broglie's wave always travel faster than light. Is this possible? In order to understand this unexpected result, we have to think matter wave in a different way. So one can say the phase velocity has no meaning as far as that the concept of matter wave is concerned. So we will introduce now the concept of group velocity, and before that the concept of wave packet. Or in other words, we can say the matter wave is not the wave associated with a single particle. That matter wave is actually the resultant of superposition of large numbers of component waves all traveling with different velocities. So we will now talk about the group of particles, and group of particles are moving with a different velocity, and that each particles will have its associated wave, and that matter wave will be the composition of the superposition of all the waves associated with those particles. So that resultant is that will be in form of packet, which is known as the wave packet or wave group. So the wave packet is actually the packet of waves coming out as a result of superimposition of these waves. So this velocity of this wave group or this wave packet, this is now known as group velocity, and it is represented by that physics. We can have some more points related to this group velocity. So a way of mathematically describe this wave group, it is actually the superimposition of individual waves of different wavelength whose interference with one another results in the variation in amplitude that defines the group shape. So the shape of that wave packet, this actually depends on the interference of those component waves, and there will be the variation of amplitude because of that superimposition. If the velocity of waves are same, the components waves are same, then the velocity with which the wave group, that wave packet travels, that will be obviously equal to the phase velocity. If the phase velocity varies with wavelength, the different individual waves do not proceed together. Obviously, the velocity is different, and the wavelength is different, the velocity will be different. So the individual wave do not proceed together, and this situation is called the dispersion of waves. And as a result, the wave group that will be different from the phase velocities of the wave, and that made it up. This is case with de Broglie's matter wave. So now let's do some mathematics to interpret this wave packet. These are A and B. These are two components waves. This is one progressive wave. This is another progressive wave, and the third one. This is the result of superimposition of these waves, and we will have this wave packet, and this inside this is that single the component wave. So mathematically, let us take this A as y1 is equivalent to A cos omega t minus kx, and the second wave have some different frequency, angular frequency as well as different wavelength. So this can be represented as y2 is equivalent to A cos omega in place of omega. Let's have this omega plus delta omega t, and k in place that k plus delta t. And we will use now law of superimposition. So y is equivalent to y1 plus y2, and then we will use this trigonometrical function cos alpha plus cos beta is equivalent to cos alpha plus beta by 2 multiplied by cos alpha minus beta by 2, and also we have these terms cos minus theta is equivalent to cos theta. So by this y is equivalent to y1 plus y2, we will have this relation. So 2a cos 2 omega plus delta omega t by 2 minus 2k plus delta k x, and cos this terms divided by half and divided by 2. Since delta omega and delta k, these are very small compared to omega and k, so one can write this delta omega plus 2 omega plus delta omega, that is equivalent to 2 omega, and 2 plus delta k, that can be also written as equivalent to 2k. So this equation can be rewritten as y is equivalent to a cos omega t minus kx, and cos delta omega by 2t minus delta k by 2x, and this is the similar to the first one. So the nature of that view, it is not changing, but it is modulated by this additional terms cos 2 omega by 2t, delta omega by 2t minus delta k by 2, and the velocity. This is actually the interpretation of that wave packet or group view, and the properties of that wave packet, this is modulated by these terms. So the velocity of that wave packet, it is interpreted by these additional terms. So let us define this terms is equivalent to, this will be in the similar to that phase velocity. So delta omega by 2 by 2 delta k by 2 multiplied by x, this can be written as equivalent to constant as earlier we did for the phase velocity. So let us differentiate this. So this vz, that is equivalent to dx by dt, it is equivalent to del omega by 2 by delta k by 2. So that is obviously delta omega by delta, and one can convert this into d omega by dk by using the definition of differentiation, by using this limit omega 1 tends to omega 2. So this is delta omega by delta k, that is equivalent to, that is written is equivalent to d omega. So this is group velocity. So phase velocity is equivalent to omega by k, and the group velocity, that is equivalent to d omega by 2k. Depending on how phase velocity varies with wave number in the particular situation, the group velocity may be less or greater than the phase velocity of its member waves. And the phase velocity is same for all wavelength as is true for light waves in the empty space. The group and phase velocities are the same. Now let us check this group velocity actually interprets the velocity of that de Broglie matter wave is or not. So let us calculate that group velocity. So for that, let's define this omega, redefine this omega is equivalent to 2 by nu, and in a relativistic case, when this nu is equivalent to mc square by h, where this mass m is relativistic mass, which can be written as equivalent to, this is m naught, so 2 by m naught c square by root of 1 minus b square by c square, and k can be also written as equivalent to 2 pi by lambda, that's equivalent to 2 pi nu mv by lambda. So this here this is the terms relativistic term, that gamma, that is equivalent to 1 upon root of 1 minus b square by c square. So k and omega can be written in terms of can be written like this. So now we have to calculate this group velocity v is equivalent to d omega by dk. So this is d omega by dk can be written as equivalent to d omega by d phi by dk by dv. So in terms of differentiation with this omega with respect to phi and this k with respect to phi, we have this relation. In order to calculate this phi z, we have to calculate the value of this differentiation of omega with phi and differentiation of k with respect to phi. We have this omega, this, and k, this. So just to differentiate d omega in terms of phi and dk in terms of b, and the value will be like this. So I am leaving this for the student to take the differentiation of these two terms. So by putting these two value d omega by d phi and dk by d phi here, this phi z that is coming out as equivalent to v, and this v is that the velocity of that particle, that velocity of that body with which that matter wave is associated. So one can say this group velocity is actually the velocity of that matter wave, because that phase velocity is different from the velocity of that particle, but here this group velocity, this is equivalent to the velocity of that particle. Now the second part of this lecture, that is the uncertainty principle. So we have now the concept of the wave packet, where this to regard this moving particle as a wave group implies that there are fundamental limits to the accuracy with which we can measure such particle position and such particles properties as position and momentum. So we have different shape of that wave group depending on that superimposition of that waves, and depending on the wavelength and frequencies of waves. And now the question is about the position of or the momentum of that particle inside that wave group. We have two waves here. This is a wave having this the narrower wave having this delta x small, and this peak is very smaller. And as far as that the concept of the probability density wave function is concerned, the physical significance of that probability density size square tells us that there is the maximum probability of existence of that particle is somewhere here. So in this narrower wave, in this wave group, the more precisely a particle positions can be specified, because the particle is somewhere here, the probability is maximum here. So one can say the position of that particle is located here, so it is accurately measured here, but the wavelength is not defined in this case. So if the wavelength is not defined, then by using this lambda is equivalent to h upon p, that is equivalent to h upon that mv, this lambda is not defined, means obviously momentum is not defined precisely. So if delta x is small, delta p will be large, and if here this delta x is the accuracy, uncertainty or error of the position, and delta p is the uncertainty in momentum. So here delta x is defined precisely, but delta p it is not defined accurately. But in the second case here, this wavelength is defined good, because we have a broad wave having a definite wavelength. If this wavelength is precisely calculated, then obviously this p it is accurately calculated, and here we cannot say about the exact position of the particle. So this delta x, the error or uncertainty in its position is large. So this delta x is large and delta p is small, and this delta p, that is the uncertainty position. So one can say it is impossible to know both the exact position and exact momentum of an object at the same time. This is the output of this discussion. So let's see again. This is a narrower wave packet, so we can have the exact value of its position, and this is a broad wave packet. Then here its wavelength is well defined, its momentum is well defined, but the position of a particle is not well defined. So it is impossible to know both the position and the momentum exactly and simultaneously. and this is known as the uncertainty principle. And according to this principle states it is not possible to measure the position and the momentum of the microscopic particles simultaneously and precisely. So there is a minimum for the product of uncertainties of those two measurements. Mathematically, one it is correlated like this. So delta x multiplied by delta p, it is greater than or equivalent to h upon 4 pi, where this can be rewritten as equivalent to h cross by 2, where h cross is equivalent to h upon 2 pi. So here this is delta p. This is uncertainty in the momentum, or one can say the error in its momentum, and delta x is uncertainty in its position. So one can say the more accurately you know the position, the smaller delta x, obviously the error will be less, and the less accurately you know the momentum, the larger will be in its error uncertainty, and the vice versa is also. And this uncertainty principle was stated by Heisenberg in 1927. That's why this is known as Heisenberg's uncertainty principle. And remember this implies only on microscopic body, just like electrons and protons, and this is not true for big objects. Now, how we can derive this relation by using de Broglie's concept of matter wave. So from de Broglie's wavelength, we have this relation lambda is equivalent to h upon p, and that wave vector k that can be defined as equivalent to 2 pi by lambda. So by putting this lambda from this relation, we will have this k is equivalent to 2 pi p by h. So we can rearrange this relation in terms of p, that is equivalent to h k by 2 pi. So when we take the differentiation or in error part, so delta p that is equivalent to h upon 2 pi, this is the constant, and that is equivalent to delta k. So delta p is equivalent to h upon delta k 2 pi. So there is one relation, since delta x multiplied by delta k is greater than or equivalent to 1 by 2. There is one simple calculation for related to Gaussian function and that Fourier analysis. We have this result. It is directly taken here, delta x multiplied by delta k, it is greater than or equivalent to 1.2. So this delta k is equivalent to, it is greater than or equivalent to 1/2 delta x, and by putting this value here, one will have delta x multiplied by delta p, that is greater than or equivalent to h upon 4 pi. So this is equation states that the product of uncertainty delta x, that uncertainty in the measurement of its position, and that delta p, that is the uncertainty in the measurement of momentum in along x direction, in same instant is equal to or greater than h upon 4 pi, which is further written as equivalent to h cross upon 2 pi. So one can write this uncertainty principle in terms of energy and time also, as well as angular position and angular momentum, and there is a very a small mathematical calculation here. So one can convert that uncertainty position, which is in terms of momentum and position, will be in terms of energy and time. So we can define this velocity v is equivalent to delta x by delta t. So we will have delta x is equivalent to v multiplied by delta t here, and the kinetic energy is defined as equivalent to half mv square. So delta E that is equivalent to 2m, and 2 will be cancelled here, so mv multiplied by delta v, and this delta m and delta v can be rewritten as a delta p. So this energy can be equal to delta p multiplied by v. So delta p, it is equivalent to delta E by v. So we have the delta x multiplied by delta p, that is equivalent to this delta x is equivalent to v delta t, and delta p is equivalent to delta E by v. So this is delta E multiplied by delta t. Then from uncertainty relation, we have this delta x multiplied by delta p is greater than or equivalent to h cross by 2. So one can write that delta E multiplied by delta t, it is greater than or equivalent to half h cross by 2. So one will have this uncertainty principle, uncertainty relation in terms of energy and time. Now one can convert that uncertainty relation in angular position and angular momentum too. So from 11th physics, we have this is that angular position, and one can write this angular position as equivalent to arc upon radius. So delta phi is equivalent to delta x by r. So delta x can be written as equivalent to r multiplied by delta phi, and angular momentum is correlated with linear momentum with this r. So delta j that is equivalent to r multiplied by delta p, because that angular momentum is equivalent to r cross p. There in 11th physics it is given. So delta p can be written as equivalent to delta j upon r. This is the relation, and one can calculate here. So now delta p multiplied by delta x, it is equivalent to delta x is this, delta p is this. So by putting this value, we will have this delta x multiplied by delta p, that is going to delta j multiplied by delta phi. So obviously we have this delta x multiplied by delta p is greater than or equivalent to h cross by 2. So this delta j multiplied by delta p, that is greater than or equivalent to h cross by 2 also. So this is the uncertainty relation in angular position and angular momentum. So for numerical problems, we can use this relation and this that relation also, and also this relation is also in used in that laser technology, laser the mechanism to interpret or to understand the mechanism of laser. Okay, so finally the summary. In this lecture, following points were discussed in detail. First, the concept of wave packet. This is the new terms to interpret that matter wave. This is the matter wave is not actually a single wave. That is actually the packet of numbers of so many waves. And now the difference between phase and group velocity. Phase velocity, this is the velocity of a single wave, a component wave, and the group velocity is actually the velocity of that wave packet, which actually really interpret the velocity of de Broglie's wave. And then Heisenberg's uncertainty principle and the uncertainty relation in different form. So thank you all, and I think this lecture is a little bit lengthy, and so you have to keenly observe each and every points and give the feedback. Thank you all.